stay? Okay, it should be done. Okay.
1, 2, 3.
Yep. Okay, one announcement before we start, just to say that there are a couple slots open this semester with some cancellations we've had for it. So if anyone wants to make a presentation here on Friday, they're welcome to do so. Just holler at me. Although I think maybe Ken is going to take one of them, so maybe we're down to one. So thank you, Ken. And so today, Bill will update us on his progress in modeling this that event.
Yes. Thank you. Thank you. Okay. Now does the technology work if I stand here and I'm not allowed to move my feet? Okay. My name is Bill Kennedy, and I'm the principal investigator on this project. And there's several people, and I'll go through some of the names. There's a collection of people here. Some have paid us. Many of them are volunteers. We now have more volunteers on the project than we have people who have actually been paid. So I'll talk about that when we go through. Here's the, wait a minute, I got this fancy device, and I should be able to use it. Yes. So here's the outline of what I'm going to talk about. An introduction, talk about, this is start into the third year of a 3-year project. We are modeling, where our task is to characterize the reaction of the population of a megacity to a nuclear WMD event. We originally proposed a megacity outside the United States as they requested, and when they came to talk to us about funding it, they said, we'd really not like to practice targeting a foreign country, so pick a megacity in the United States. There's only 2 megacities in the United States. One is New York, and the other one is horizontal, LA, and we went with the New York. So that's the big background. We're modeling, well, I'll get through some of these. So we're building an agent-based model. In other words, we're modeling the individuals in the megacity and surrounding areas at the 1-to-1 level. So we will have agents representing individuals. I'll describe how we do that. They're going to be heterogeneous. They have their own characteristics, and we'll play with those. This is a standard Department of Defense quad chart. We've been using it without hardly any change from year to year. Okay, so the objective is to characterize the reaction. And they mean the reaction measured in a few number of days after an event. To simplify our task, we said a no-notice event. So there's no preparation, nobody's starting to get ready for such an event. They are where they are when the weapon goes off. Makes the modeling much simpler. We proposed, and we can talk about other options, but we're going with a no-notice disaster. We finished the second year in the end of last academic year. Then we had the summer after that, and we're now into exploring and characterizing. Big picture, we're dealing with 3 areas of this world: the physical environment of the New York City area, the agents themselves, and their associated social networks. So we're going to synthesize the agents, we're going to synthesize the environment, we're going to use as best we can real information about we're going to synthesize the agents and their social networks, and we're going to use as best we can models of the real environment. We're going to do this in layers, and they all lay on top of each other and interact between them to represent the entire process. So our region is New York City and surrounding areas. There's the idea in kilometers and in miles. For those of us who still think in miles, it has pieces of several states, but this is Manhattan. This little tiny spot here is Central Park, and Manhattan is only about that big by that wide on this chart. Okay, so where we are is we've done the literature search. We have an idea of what we want to make happen. We have collected data on the population, and we needed to synthesize the population. At the end of the first year, we had piloted some population modeling efforts, And in the second year, the challenge was to scale those up to 23 million people. That presents some challenges, and I'll talk about that down at the bottom. But I'm going to talk about the scaling up, validation of the model as far as we are so far, scaling up the agent placement within the model. This is describing the agents. This is getting them inside the model, trying to deal with their behavior at full scale, challenges, and future plans. Okay, so we've been working basically to this flow chart for quite a while. We start with building a road network as the skeleton to hang our agents on and have them move on and run from, things like that. Then we needed to create their, and I go back through, after we had the road network, we needed to create the individuals. We're going to get to this. Create the individuals from, we use census data. Talking too fast, I know. We're using census data at the tract level. A census tract is approximately 4,000 to 8,000 people, relatively very small scale. And we have descriptions of the people who live in that census tract. The actual people, we synthesize artificial agents representing the same characteristics. We have their age, we have their sex, we don't know what households they're in, but we know how many households there are. So one of our challenges was to synthesize households, organize people the same way they are organized in real life, have our agents represent the same kind of thing. And then we had to create I talked about creating households, but they also need houses. We need to know where they live in this environment. We only know what tract they're in. We have schools, talk about how we were modeling schools and workplaces.
What are you working with?
We are using the Mason system. We're operating in Java. Sorry, should have described that. So again, this is the entire agent, and this is the connected road network. We thought it would be easy to just have, to bring in road network, and then life would be obvious. Our cars don't go off cliffs, hopefully, if you're dealing with a navigation system. But it turns out it took a while for us to be able to get to one road network where our vehicles or our agents could move around on that road network. Had to wrestle with things like roads are connected if they're less than a meter apart. Why aren't they just, it seems like it should have been automatic, but we had to play with that. Okay. Sorry, we're not dealing with over or under or through passes. Yes, there are some interesting challenges that we're getting past. Let's talk a little bit about the population. 23 million people in this area. This is the density at the different tract levels. So you can see, yes, this is the New York and its boroughs. That's Manhattan right in there, and its boroughs around, out to New Jersey and to Connecticut. I'm going to stop that because it freaks me out. So when we piloted populating our agents, we're looking for code to build this on, and we took we looked at a couple of different existing models in Mason, and this one has agents placed on roads and it moves them around. That was one of the ones we explored. We ended up using what is referred to as gridlock as our basic model. It's one of the models available in the Mason system. If you go get it, it's a demonstration model. So this is one tract. We knew how many households there were. We knew how many workplaces there were. And now you have to put them on there. Anywhere. We put households on secondary roads. We put workplaces on a little bit higher roads and on intersections and secondary roads. So you can see the different colors here as marked over there. And we put schools where they are actually located. We didn't synthesize where to put schools. We used their actual latitudes and longitudes. There's only a few schools in this entire area, but we took that file and imported it in. We've now scaled it up, so we have placed our 23 million people in the second year. We scaled it up to 23 have homes, workplaces, and schools throughout the entire region. This is an idea of what it's like when you plot all the homes, workplaces on Manhattan itself. At the tract level has quite a bit of information about how the people are arranged in there. We synthesize the data in the intent to we sent to our validation process, RTI, another synthesized population also using the 2010 census by RTI International. They were willing to let us use their data. Their data is used by NIH, these model community survey that the census added after 2010. So here's an attempt to show we have 7,100 tracts in our area, and I want to show you our area and the CI and the census data, and then later our censuses compared to the RTI censuses. So we're going to be a little bit creative in how to process this. So this is trying to show the differences, the errors between ours and the census information on 4 different measures: the average family size, the average household size, which is a little different from families because there are other people living there, number of households with minors, number of households with people over 65, listed as seniors. So we didn't do too bad on average family size or household size. We're having a couple of outliers when we variations when you deal with households with minors and households with seniors. And they get fair large. That one off in the corner is up there at 8 times the number in one specific tract. We discovered some of the things that we found were you may not realize it. I didn't realize it. How many on my team realized it? But census data, we take census data and we say, this is the people. It turns out census data is where everybody is on April 1st of the census year. So where are all the bright young 18 to 22-year-olds? At home. They're concentrated in locations. And some of our tracts have colleges that upset our numbers because it's not the same as where people actually live. And same for some old folks' homes, to use colloquialism. There are some concentrations. So our data isn't perfect, but we know how it's different. So here is each tract and its difference for 2 different measures, households with minors and households with seniors, the ones that were a problem. And you see that number, that high number, was one specific tract out of the 7,100. And there's a couple of others that are also a little interesting. Here's on average family size and average household size. We would like it to be right around the 0, but most of it's within 10 or 20%. Here is a different way to present this information for comparison. And so these don't look too bad, subjectively. So I can now do it by groups of tracts. And so this is what it looks like for all the tracts that are part of New York. And this is Manhattan. This is a little bit different. No. This is all our agents that are New York voters, citizens, not just Manhattan. Manhattan is just the tracts right about in this range.
New York State within your area.
Yes, we didn't go all the way up to Albany or, I'm sorry. So this is comparing them within the state, and we get different lines. There's 2 plots here. There's one on the absolute, and then it's plotting both I didn't go over that, I should go back. The red and blue are the two different censusized populations. The red is ours, the blue is the RTI's censusized population. So they're hanging in there, but it's difficult to measure each one. This is doing a measure of the difference between the red and the blue, ours versus RTI's synthesized population. And we can do that for each one. And just a few household sizes. Number of people in a household. No, this is just flat difference in the averages. Okay? And when we get to those two little pieces of Pennsylvania, which fall into our region, not very many tracks, and they're not terribly far off, except a couple in here. Okay. Trying to put all that together and make sense of the whole thing, the vast majority are within 10% of each other, so we think we're doing okay. But it's kind of a subjective assessment. We recognize that. There aren't official tests for something as on this kind of scale, unless Billy's got an answer. Yes? We have a set of heuristics that we used to group people into households on the age difference between the male and female head of household, the range of the kids that would be for people of approximately that age. And there are 10 or 11 different types of households. The 10 are as defined by the Census Bureau, and the 11th is an institution where we concentrate a whole bunch of people, not as a household. No, we created the people first. That's based on census data, straight census data, age and sex, and tract. That's all we know about them. Then in a tract, we organize them into households. I could go all the way back to the little flow chart. Once we get them in households, we can now assign them to houses. So we now know where they live. And in the tract, we also have their workplaces. So we can assign them to workplaces which are locations in the same tract or any tract in the area. And we have some that commute reasonably far distances. Does that make sense? Okay. We got to get to the interesting part. We also synthesized a couple of networks for our households. So here's an example. There's a 57-year-old male, 65-year-old male, 57-year-old female, and the X and Y dimensions mean nothing on this chart. So here's a household, a 57-year-old male, a 56-year-old female, and a couple of teenagers. And that we connected everybody in the household together. We said they're a clique, they all talk to each other. We're not dealing with family issues. We then connected them through their school location and work locations to a sampling of their coworkers or other students at the same school. So they've got a social network associated with where they spend their time during the day. And so you can see the 57-year-old male has a lot of girlfriends, and the 16-year-old daughter has a lot of all male friends. We synthesize this. You can write stories. You can write 23 million stories just from the synthesized population data. Okay. And we have a student who's trying to do that as his PhD, to be able to take an agent-based model and tell the interesting stories for an individual agent as it runs through, is processed through the model. So here's that social network, the household and its social network And this is a plot for the other agents in the same tract. So this is the 4,000 to 4,000 to 8,000 other households. If we show their network, then you go, okay, everybody's connected. Yes? We have, okay, and it gets to be interesting. The part that's not interesting is, with the information that we have at the tract level, we also know what tracts the people who live in that tract commute to for work. So we're not randomly assigning them to other tracts. We're doing it based on the census information. On their schools, we put in the actual schools and we placed them in the closest school that had room for them, and then we moved farther and farther out, which causes challenges. You know, do they cross outside of a tract? How do we deal with that? We found ways to deal with it and make it work. This is the network, social network of one county. It's a hairball. It's absolutely useless. So let me try other ways of describing. That's what? That's no moon. Yeah. You have a bad feeling about this? Good. So let me try to find some other ways to describe these networks when you get to something that is bigger than you can visualize. So we can start dealing with just counts and information. So we got 23 million nodes, and they have a number of edges connecting the different individuals together. We have a number of households, number of workplaces, number of schools, and we deal with our social networks, edges, based on, are they associated with households, workplaces, or schools? So we can describe them. We made these people up, so we know everything that's in the model about them by design. Sure. You tried before. 23 million? Yeah. I will show you the degree of separation. The degrees, not the separation. The degrees. Here's the degrees for individuals based on household networks. And an individual can be a household as well as having other people associated with them. So here are households that nobody else is singleton house, 2.4 million singleton households. Couples, 3.5 million. And 3, 4, 5, and it goes out to two households with 12. It's individuals, yes. This is within the household. Sorry. Yes. Wrong direction. Repeat the questions. There's more networks. This is only one network. This internal household network.
So household edges, you have 18 million households.
Just to give us some perspective, I think the question is sometimes related to how people think about networks and our department, which is that they're scared of the family networks, not scared of
Right. We're connecting everybody to everybody in a family.
So none of the networks in this model are scale-free. These are real networks where you actually tie in. So we did the workplace and school, we looked at small buildings. We created small networks. The algorithm number is 5. And so that's how we got to our
Okay.
Have no edges in this network, and two-person households have one. That would explain the.
Right, the same
Yeah.
are isolates.
Same points. Okay. So we've been discussing what these charts are showing. They're showing networks among individuals within a type of network. This one is workplace networks. For those who work outside of the household, they're connected to a workplace network. And this is the school network for our synthesized agents who are between 5 and 18 years old. They're assumed to be at school, and they have this collection of edges. Sir. Workplace network. Wrong way. No, the question is the degrees in the workplace network. Doesn't seem to make sense because it seems way too low. You're assuming all 23 million people are in the workplace. It's more like half the people go to work. They either work out of their home or they do consulting or something as individuals, but those who have a place that they commute to that is their work, there's a smaller number than the 23 million. Correct. Vast majority. Yes. Correct. These are not directed. Yes.
One edge makes
two.
So you have to take every
Correctly. Thank you. We lost the stream. It's now a river. Did you look at the table?
No, stop. I could just keep going. I'll fix it.
Okay. Okay. Schools, we got there. So that's the social network. So now we have people, homes, work, schools, and social networks to flesh out our agents. Oh, okay. The networks that we've been describing, the households, the workplaces, and the school networks, are static at the beginning of the simulation. Since we're running a relatively short period of time, we're not letting people get married. We're not even letting them die. Well, we're going to kill them. We're not changing these networks of these networks. After the event goes off, they're going to develop a dynamic network associated with the people who are going through the same thing they are. That's a totally different network system, and we will deal with that after the boom. Okay, so we synthesized and placed the population on a map. This is a couple of counties up north. We did that in the first year. In the second year, we put all 23 million agents on a map. This is 10%. There's a red dot on here for every 10th person to give you an idea of how dense. Now I can make these dots very tiny, and so you wouldn't see it, but this gives you an idea of the density of the people in the region that we're talking about. This is our synthesized people. We get to see how large they are. This is not, but it's related to the tract population density, where the tract color indicated the density in that individual tract. Up here. Yeah. Okay. In our model, This is zoomed all the way out and showing you all the agents. We can zoom in many not orders of magnitude because it goes in by powers of 2. So this is zoomed in 64 times to look at Manhattan itself, their Central Park. And yes, there is some interesting anomalies. Part of those millions of stories you can tell about New York, there were people the census reported lived in Central Park on April 1st, 2010. It ended up being a little story in a newspaper somewhere. But here's all the places that people live in on Manhattan and across the Jersey Shore. I said the second year was about scaling up. Now let me tell you the to maps with the synthesized and of the entire 23 million people. So to produce 230,000 agents, 15 minutes. Do 2% of these is to do piloting, to testing, to explore. We don't generate the whole population every time. We deal with smaller sets, and one of the challenges is just the computing necessary to scale it all the way up. So, is that the only, sorry, no, I'm going to talk about several others. And if you've got more after I describe some, I'm all ears. Okay, so we're trying to get to the behaviors. So let me talk about some agent behaviors and trying to get them to full scale. Those 2 counties that we had up there, we had agents moving around at random on the road network. Okay, they move. It's a little creepy. Whoops, go back, go forward one. There they are. They're randomly moving along the road network, and when they get to the end of what they're interested in doing, they turn around and go back the other way. But you get to see a little bit of traffic, and they're just moving. Okay. Yes, it does slow the vehicles down based on the density of traffic on that little tiny segment of road network. Yes. Okay, so I'm up here to agent behaviors. So we're trying to get to goal-directed behavior. We're going to start off with temporal. In other words, they're following a routine. They get up at a certain time, they drive to work, they are at work for a period of time, and then they come back. We know that some of the people take kids to school and then go to work and come back to school and back home. There's other patterns of what people do. I got a picture of that. Where is my picture? There it is. Sorry. So here's a collection. Couple of things. This is notional. This is not precisely what we modeled. We didn't say that only males with a single child take the child and go to work, go to office work and go back, and that single women work in factories. We didn't, that was not part of the plan. But you notice it has everybody at home at midnight. That's not true. We're talking about the city that never sleeps. So some of these need to be turned around and go to work at other times. We have collected data on that over the summer, and we're trying to put that into the system. And this is giving you some ideas of the variety of normal daily behaviors just driven by a clock. There's actually some data on that. This is survey data collected on what people spend their time on over a 24-hour day. And it's slightly shifted because they started at 6 in the morning. But the outside gray is sleeping, and this part, the smiling face in the lips in the middle, I guess, is their time at work, and there's what they're doing the rest of the time. That's the kind of data we would like to get to. This is what our model has. This is modeling only 763 people who live on Manhattan. It's a test case to demonstrate that the model will work. So they are sleeping from midnight and we used a Gaussian for what time they leave home, and so some of them leave at 2 in the morning to go to work. And they commute into work. This yellow is difficult to read down here is the morning commute, and this is the number of people at work. One of the things not anticipated when you put agents together and you say life is simple, we're telling them exactly what to do, but if you use Gaussian distributions, we found out that we had some people who never made it to work before it was time to go home. That was not a case that we had planned on, so we had to put in a couple of special cases about, okay, if it's time to turn around and go back home and you're not at home, start heading home. So even if you were commuting in or you're at work, you could turn around and go home. It does, doesn't it? So this is what it looks like over a 24-hour day. We are plotting this at 1-minute steps. The steps in our model are 1 minute, and you think that's really fine grain and unreasonable. If we're only modeling a couple of weeks at most, that's not that many steps, because 770 is noon, 1,440 minutes in a day. That's not too bad. So here's 3 days, and then on the 3rd day something happens, and a whole bunch of people die. So we now have in the model a bomb going off and killing people. This is just a prototype. We're getting started in it, but we're now modeling it and counting, and we can tell what the effect is in a very gross sense. So when we choose to set the bomb off and where we choose to set the bomb off is obviously going to be a big part of the impact, and we'll explore some options on that. But it's running. Okay, so challenges to get where we are and how we've gotten past, or how we are dealing with them, or how we have swept them under the rug. First, scaling up. I gave you an idea of the time. The other challenge is researchers themselves, us. So we're going to step through each one of these. First, we had the challenge of generating 23 million heterogeneous agents. And we used several heuristics to put the households together. We used what we had as available to decide when they leave home and go to work. The arrangement of the what their normal work hours, we have data on what types. We have data on the normal work hours on a weekly basis for the people of the country, the US, and some information about the people of New York. We're going to synthesize and assign people times to leave the house rather than have them all intending to leave at something like 7 o'clock in the morning, to make that a little bit more realistic. The whole point of their normal behavior is to figure out where they are at the time we set the weapon off. And you've seen, go back, this goes back. You've seen that we have quite a variety of counts of people at different locations, whether they're at home, whether they're at work. Again, not again, but we are also simplifying our challenge. We're only modeling the work week, and we will probably only worry about the normal business hours type time frame to have the weapon go off so that we have an idea of where people are. New Yorkers do all sorts of interesting things after work, and we have some data on that based on Twitter information, but we will get to that in the future. So, generating those 23 million people. It has not gone well. It's been a challenge. We've run across things and had to go back and undo them or redo them. And so we're trying to get 23 million people, one-time calculation of what their initial conditions are. Then we run the model, but we still have to get them to behave. The next challenge is getting those agents to move on a reasonable schedule taking the heterogeneity and leaving home at an appropriate time, being at work, etc. We also need to model first responders, the people who go in the opposite direction of traffic, who are headed toward the event rather than away from the event. And over this summer, some of our helped us find all the hospitals, all the police stations, all the fire stations in the area, and so that we can put them on the map, identify who is commuting there, who's working at the hospital, or the fire station, at the police station, things like that. I'm going to call those part of the first responders. I'm not modeling guard headquarters and things like that at this point. Okay, so I've talked about why we do this. So here's how we're dealing with the challenges, and if you have ideas, talk to us. We're going to prototype using toy models. Keep it really simple, make sure it works and it behaves. Okay, now take it and put it in the big model. We're going to explore behaviors with small numbers of populations, like focusing only on the people who work in Manhattan and commute in from all sorts of places, or who live in Manhattan and commute out, or sampling every 1,000th person or something like that. I'll tell you one of the mistakes I made is I said I need every 1,000th household represented commuting. And so I organized the population by households and selected the first person in each household. And the first person in each household is not necessarily the oldest person in the household. They were assigned at random, maybe a 5-year-old who's out there driving that car. So, explore behaviors with small populations. As much as possible, we want to do one-time static calculations, in a sense, offline, and then load them into our model, rather than having our model go through the entire effort. We're working through that. Some of the models that I'm showing you so far are dealing with and recalculating everybody's path based on the latitude and longitude they're starting from and going to. Those paths are fixed, their commute path to work. We shouldn't have to recalculate that every time. So we should get some efficiencies from that. And as much as we can do one time offline or prior to running the model, we're trying to do that. We try to get some help from some computer science concepts. So here's the two that we've picked up so far. We're modifying the representation of the infrastructure to use hash tables rather than have a flat file of 23 million people. We'll have a hash table that says if you need an ID, we can go straight into the hash table. You don't have to search through it sequentially. Seems obvious. We're also doing that for households so that you can sequentially go through the households and search down the line of the agents associated with that household. Same for workplaces, because we're going to have to pick people up and we're going to have to figure out where their workplace is. So we're trying to simplify some of those things. Hash tables are a simple idea of pre-calculating an index into a large array based on a single key or a more complicated key, but being able to go straight into it almost like it was random memory, random access memory. The other thing we're doing is one of our volunteers, a high school student who goes deep into Java and spends his nights and weekends playing with code and volunteered to work on this project. He also took an agent-based model of city evolution to his school science fair, the regional science fair, and down to Richmond. He didn't get to go to nationals. Mason is a wonderful system that has separated the visualization from the simulation itself to try to get both of them to run as fast as possible. So you can run it headless with no visualization, and it runs very fast. If you want these plots, if you want movies, you have to run it interactively. So we couldn't run it on the clusters and get movies out or even plots out. We could print out unreasonable amounts of data and then go build our own plots. The high school student went in and played with the code and modified the code to be able to produce the movies headlessly. So now we should be able to run Mason on the cluster and have one of the outputs be a movie. The scary part of that is it's like a 15-second movie of agents moving relatively quickly is a multi-gig file. So running them for a couple of days, we're concerned the file may be bigger than we can get off the cluster and back to somebody to use it. We'll get to that problem, looking forward to it. So these are the two things that we've dealt with so far. The same high school student looked at the A-star algorithm that calculates paths in Mason, the A-star algorithm that has been in place and used by everybody for a long period of time, and found two things that he thought would actually speed it up. In one case, it calls for a calculation and assigns it to a variable, and the very next line calls for exactly the same calculation and assigns it to a different variable. Could have just done the assignment as a straight through, rather than recalculate it. That's not going to save a lot, but if you're running millions of agents and doing that over and over again, that's kind of significant. Yeah. Right now we have magical vehicles that any number of people can ride in and they pass through each other. Because our road networks are edges between nodes. They aren't directional, although correction. Our paths through the network are directional, so we can go from point A to point B. But our road networks are one lane wide lanes, but one lane roads. We have not gone beyond that. Okay, let me repeat the question and break it apart. The question is, would the EMP from a hydrogen nuclear weapon destroy all the cars within the blast zone, and the electronics, excuse me, just the electronics, just make them dead, etc. Two things. One, the amount of, or the strength of an EMP varies with the altitude of the weapon. We're dealing with ground burst to be dirty and terrorism oriented. So we have very little EMP to deal with, only in a small area. That's most of that. So we get to invent our scenario to give us them as clean a process as possible. Yes, we're still looking at an efficient device. But H-bombs are much bigger. We're exploring for this effort a 5 to 10 kiloton weapon at the ground level. Yeah. So yep, we're dealing, because our model doesn't have subterranean, they're just moving. We're probably, the blast effects that we have modeled at this point just use radius from ground zero in 2Ds. Yes. It is going to be limited, but even a 10K, the significant blast area which would take out high-rise buildings is almost the width of Manhattan Island. Oh, it's small compared to 100 megaton blowing up the entire region. Population. Yes. The website Nuke Map predicts for 10 kiloton in this kind of range, 250,000 people killed and about 350,000 injured. Yes, out of 23 million, I wouldn't want to talk to them and tell them they're peanuts, but it is a small number. And
Well, it's a large number of survivors now. Problem.
yes, and we're after their reaction. The dead don't react. So we'll get there. So those are the ideas that we're looking at. If you have other ideas of how we can improve the efficiency of trying to scale this thing up. I wouldn't say huge. I don't, it's not the code that is the scale problem.
Developers that working with large scale database models.
Yep.
Talent want to you should read the sales brochures if you know your software. Nobody's ever done it. You've got a good candidate for trying that.
The British, no, my sponsor pointed me toward the British Ministry of Defense. The British Ministry of Defense pointed me to an online gaming organization, company, who is spending millions toward billions of dollars by the name of Improbable. And they say they can run 25 million agents live with people driving them in an interactive environment that they've basically, and this is part of the reason I didn't go with them. They say they've basically solved the ability to separate different regions and not have them interact with each other, so that they can model those scales and have it effective. Their product is the hardware it runs on and the environment. So you have to write it in their code, their way of representing all the objects and agents and their behaviors. And we thought that sort of violated our intents of being open. No. Okay. Okay. Nice. How complicated are they? Do you have a feel for how complicated they are? Oh, this is a transportation model? Pilgrim. Okay. Very nice. Yes, definitely. Okay. Yeah. I fully agree that that's certainly better than what we're playing with, but most of our development is being done on percentages or fractions of a percentage of the overall population. To make sure it works, I would describe our system at those low scales as interactive. And by interactive, I mean, I remember what my question was when the code comes back with an answer. But once we get the behavior sorted out and we go to, in a sense, a production mode, I don't know that I mind if it takes 3 or 4 days, especially if I can get the movie out of it and it's manageable. Yep. Yep. We have not yet. I started with the uniform distribution and didn't like the shape of the curves that produced, because everybody left and got to work and everybody came home. Very rigid. So I did a small variation, and it hasn't been. We know what the average commute is. It's like 40 minutes for everybody working in the New York area, and we are wrestling with setting reasonable speeds that the agents move and comparing that to a 40-minute commute, or do we play with a different dimension and get them to behave, but now their speeds aren't realistic. It's kind of, are we modeling the commuting, or are we modeling they get to work and now we blow it up? We have information on that, but we don't have it at the individual level by any means. I don't think we do have a standard deviation on it. Yeah. Yeah.
So, the town manager is right.
Yes.
Well,
Well-
the
Not all of them.
No. No. Also produces very valuable students who we've lost. Lost one to a startup in Silicon Valley, literally off, and hopefully will finish his degree. We'll see. And we've lost another one because of trying to focus on the schoolwork as opposed to the project. This can be seductive, and you can lose track of time and forget that you're supposed to be working on a dissertation proposal. That's not altogether good. So looked at creative ways of resourcing some of this. I mentioned I had a bunch of names up on the very first slide. I can't casually flip back to that. But our sponsors, the military academies, the country's military academies, send him folks over the summers. And he's supposed to do something with them besides have them run the Xerox copiers. And he said, would you be interested in taking any? And I said, yes. And I got 3 behavioral systems students from the Air Force Academy for 3 to 5 weeks over the summer. And they collected information on the normal work hours, the distribution of start times for the school systems. And you probably all deal with, or you might deal with one besides George Mason, an elementary school, middle school, or high school, and think that there's an ordering of when each of those schools starts so that the bus systems can be used for all of them. Turns out the different high schools, the different states have different ordering. In some cases, it's the youngest who have to be there early. In some cases, it's the oldest that have to be there early, and everyone is different. And we're finding that that's true in the New England area around New York. And you go, okay. Yeah, I know. But you'd think there's only 3 possibilities, but then every household is different, and yeah. So we've had some challenges, but they've collected that kind of information. They were undergraduates who were here for part of the time of the summer. I mentioned one, and the other one I had coached on his coach. I had talked to a couple of times about his science fair project, and it occurred to me maybe he'd be willing to do it. Sent him an email, and he jumped at the chance too. So we had 2 high school students work with us this summer. I teach computational data sciences, computational and data sciences courses. I'm teaching a freshman course that I have at the moment, and one of the students mentioned that they only needed this class to graduate in December, 3 hours, and they were bored. And I said, I got an idea. And so she has now collected, she turns out to have a GIS background, she's collected the information on the police departments and the fire departments, and we are going to be incorporating that information into our model as well. So, talk about the future, the plans. I finished reasonably on time. There's a famous book from the late 60s, early 70s called The Mythical Man Month. Fred Brooks said, if you would like experience working on this and join us in our publications, we would certainly entertain us for reminding me of that. Okay. So that was third year, the work up to this point. This is what we're doing this year. We got to get the model validated with the normal patterns of behavior, the commute times being reasonable. We need to model the event itself and how that gets spread through the networks to all the people, because we're talking about relatively small steps and above. Their first concern is physiological needs, rest of their family, potentially friends, and then they start thinking about escaping. We're not allowed to yell fire in the JC. But when I was working at the Department of Energy, I got allowed to do something not long after, not too long after 9/11, a couple of years afterwards, and we needed to have a continuity of operations plan for our group, like many parts of the government. And I asked if I could get everybody's attention at the beginning of a staff meeting, and my boss said yes. And I said, you don't know. Let me describe before you say yes. And he said, sure. So I came in late to the meeting, anxious, what is the term? Excited. Excited and said, 2 bombs have gone off in the metro. We seem to be under attack again. And the room erupted. It took us 20 minutes to a half hour to calm people down and tell them it's not real. And they said, that's exactly what they'd say. No. Everybody in the room, not everybody, almost everybody in the room was trying to call their loved ones to say, have you heard, what have you heard? Are you okay, etc. As a result of that, I have realization of why we have an internal review board to keep us carefully and behaving in our experiments. But the group also set up an 800 number for the group out in Germantown. Department of Energy has a headquarters in right across from the Smithsonian Castle, and it has a site out in Germantown, which was intended to be far enough out to survive a nuclear weapon. We set an 800 number up, and the message on the 800 number, if you called it, was basically, we don't know that there's an event going on. If you think there is, please leave a message and tell us what you know, and tell us where you are and how we can get in touch with you. So their family members could call there and get that information. And we would, if something went off, update the outgoing message that says, we've found all the people in the branch, we know where they are, and everything's fine. We had a bomb scare 6 months, 8 months later, and in the middle of running around with our heads cut off, we said, ooh, we got an 800 number. Some of us were not in the office at the time, and we called the 800 number, and the 2 members of our 15 people group had called in and said they were fine, they were off at this building, they were at home or something like that. Might be something people consider. Okay, too much, but this is the kind of thing they dealt with. First, are they okay? Connect to the family members, and EMP is going to be a player in that, and then think about escaping. When we talk about escaping, we're figuring that our agents will be, if there's a single weapon that goes off, everybody knows which direction to go, away from the weapon. If they, our literature review of how people behave in disasters has found that people are amazingly pro-social in the following sense, or because of potentially. A disaster puts us all down to be equals again, just humans. And people will help another human who is calling for help, needs help, etc. There are very interesting stories of heroic behavior by people helping other people out of the Twin Towers in New York. People being carried down tens of flights of stairs. There's also some fun stories about people getting down to a certain floor and saying, what in the world am I doing in high heels? And everybody dropped their high heels at that point, and from then on there aren't any more high heels. Okay, so we're going to do experiments with 10 kiloton in Manhattan, and maybe we should do it outside as well. We've been advised by our sponsor to keep it unclassified because this is basic research. So they pointed us to the 1967 study that is out there and is available as PDF, or you can buy it on CD, or you can buy a hard copy of it. And so we're using that for the weapons effects. Modeling it in concentric circles of fireball, blast zone, fire zone, things like that. Keeping it simple. We proposed a wide variety of extensions to this project to our sponsor at the annual review in June, and the sponsor said, I like number one. We said, okay, we'll work on improving the fidelity of the basic research model. The sponsor we've offered them a statement of work, they've liked that, they're considering that through their process. So there is a reasonable chance we may get 2 more years of extension to continue making this a better model. It's under consideration. So we've started modeling behaviors. We're finishing up the second act, moving into the third act where we resolve all the problems that we had in the second act, all the plot challenges. We're trying to get our arms around those challenges and get to modeling actions. We're working on performance for now so that we can get to an answer, and then we'll work on fidelity. Those aren't pretty, but that's what we really need to do to get moving. So thank you very much. Any questions, suggestions, recommendations? We're all ears. Okay. Are we modeling fallout? Yes, we will model fallout. And simple weather patterns. The basic fallout is that there is for a 10 kiloton ground burst, there is a plume that goes in a direction depending on the wind, but it goes a reasonable distance and has fairly high radiation levels that will be life-threatening to people. Unfortunately, we don't have any sensors ourselves to know we're in a radiation zone. It's like sunburn. If you're out and you realize that your skin is turning red, you know it's already too late. It's going to be a really bad night. Same for our agents. They're going to get sunburned. Yeah. Yeah. Why we didn't just modify those? One, we're dealing with a no-notice event rather than a storm that comes up with some notice, at least to some degree. Hurricanes might have been interesting. Tornadoes might have been interesting because you're very short. Or tsunamis, definitely, but they're very coastal and very localized. The interesting is the scale on those other examples. We have approximately 1,000 tornadoes reported a year in the U.S. And 1,000 tornadoes is approximately the same size of energy as a 10 kiloton weapon. To put it in scale, 1,000 tornadoes going off in one location. But there's lots of reasons. No, they're not dealing with those kind of scales. I need to get, question? Yes, we have their final report, and we've looked at their transportation model. We'll consider it. Wait, what is activated that is re-radiating from the people? The belt buckles? Okay, they contaminated. Okay. Yep. Certainly. We're still at the point of setting up, trying to figure out how to model those checkpoints around the area. And our sponsor is interested in how far away from ground zero do they need to set them up. And I can send my sponsor there because they were interested in the 100 megaton interstate warfare weapon, and do they set up that checkpoint in Ohio as opposed to on our charts. We're not there. But the report is available. I've got a copy of it. Yeah. Yes, we're not dealing with the classified. Yes, sir. Not yet. Not yet. We're still developmental. We're not going into production. It's basic research. You're going to cut it? Okay. Okay.